It's time to finally talk about your guys' favorite chemistry concept. Hooray! What, you guys don't like Vesper? Come on. Vesper's amazing, dude. Other than the fact that you had to memorize 600 million different terms for the same hacking thing. God dang it. Hello everybody, I'm Kara, and today we're doing Unit 2 of AP Chemistry, dude. It's amazing. And today we're going to be talking about molecular and ionic compound structure and properties. So this includes all the yucky stuff, Vesper, hybridization, polarity, all that yucky stuff, but don't worry, it'll be fine, we'll get through this. So I thought of the big brain strat of posting the periodic table within my Photoshop so I have a little bit more space. Hopefully this works, and I can also shrink the P table as much as I want. Epic. So anyways, let's begin. Okay, so the first thing we gotta talk about are chemical bonds. So basically these boys are the bonds that hold together molecules. So the first important one that you gotta know are ionic bonds, okay? Now these guys form between guys in the first two columns and guys in the last two columns, generally speaking. There's some exceptions. Mainly, as long as the two components are ions, it makes an ionic bond. So even if you have polyatomic ions like AlNO33, this is also ionic bonds. Even though there's multiple things coming together and there's ion, it is still an ionic bond between the Al and the NO3s. So basically what an ionic bond is if you have an Na and a Cl, right? And you got your 1 valence electron here and you got your 7 electrons here. Basically what ionic bond does is it takes it completely away from one and gives it completely to the other. So in this case, sodium will completely lose its electron. Okay, we got a completely lost electron, and now this guy is plus, this guy's minus, and now they attract each other. Now before we even move on to the other types of bonds, we first got to talk about Coulomb's law because that applies to whatever charged particles you might be dealing with. So basically what Coulomb's law says is that the force between two particles is kQq over r squared, Q1, Q2. And basically, as this force becomes stronger and stronger, it's harder and harder to pull these molecules apart. So basically, the measure of how strong the ionic bond is called the lattice energy. So in AP Chem, you really don't have to actually calculate the lattice energy, you just have to know what it is and how it changes with charge and distance. So as you increase the charge of the ion, as it goes up, your force is also going to increase, so your lattice energy is going to be increased because it's so hard to take apart those ions. And then the other thing you got to know is how distance affects it, right? So if you bring two ions farther apart, they exert less force on each other, which is why it's in the denominator, and that makes sense, right? If you bring two magnets really close together, they push each other out faster. So it's basically the same concept. So know this, increasing charge, increased lattice energy, decreasing radius means increased lattice energy. So a question they really like to ask is which has a higher lattice energy, MgO or LiF? And basically, generally, you should always look at the charge first because the charge contributes a lot more to the force. So in this case, Mg and O both have charges of 2 minus because Mg has 2 valence electrons, O has 6 valence electrons, so they want to give each other 2. But then in LiF, it's only 1 minus and 1 plus, 1 plus, 1 minus. So the Mg and O, they have so much more charge. So their lattice energy is going to be way more strong. Even though lithium and fluorine have smaller atomic radii, the radii doesn't matter as much. Because the ratio between the radii is not a factor of 2 or anything crazy like that. So whenever you deal with lattice energy problems, first check the charge, and the one with the greater charge is going to have the greatest lattice energy, and then after you do that, then you have to check the distance. First charge, then distance. For example, right, if you had LiF and NaCl, NaCl are farther apart because their atoms are bigger, so they have the same charge, so in this case, NaCl is going to have lower lattice energy because they're farther apart, so they exert less force on each other. Okay, why the heck is this nonsense relevant, huh? Well, you could determine the relative boiling points of things just by looking at lattice energy, because in order to boil something or melt something, you have to overcome these things that hold the atoms together, right? So if you look at our example, again, we had LiF and NaCl, we can automatically tell that NaCl is going to have a lower melting point and boiling point just because those forces holding them together are so weak. So it's so easy just to break them apart and make it into a gas or into a liquid or whatever. And then also with solubility, NaCl is going to be way more soluble because it's so much easier to break the atoms apart from each other. So technically ionic bonds are intramolecular forces, which are basically within a molecule. And that's what the chemical bonds we're talking about today are. Don't be confused with intermolecular forces, which are between different molecules, not within the same one. Alrighty, very cool. Let us move on to covalent bonds because ionic bonds are boring. Come on, you know that. So while ionic bonds form between metals and nonmetals, covalent bonds generally form between two nonmetals. So like a carbon-carbon bond is probably going to be a covalent bond. So basically what a covalent bond is if you have two C's, right, carbons, they basically have 4 valence electrons. Then what they do is that they share 2 of their electrons, so they both get closer to reaching their total. They both want to reach 8, right? So if they share these 2 electrons in between them, now they're at 5, okay? They're getting even closer to 8, so this is good. So that's basically what a covalent bond is, sharing 2 electrons. So it's not one completely snatches it from the other like an ionic bond, it's sharing the electrons together. Okay, now covalent bonds are way more strong than ionic bonds, right? Because like both atoms are holding on to their own electron, right? Well, technically they're not, but like you could think of it as they're both holding on to both the electrons, so if they try to separate, they're both trying to hold on for dear life. So that's why they're covalently bonded, that's why it's way stronger. Okay, so covalent bonds aren't really that interesting. They get more interesting as we talk about Vesper and hybridization and all that. But let us talk about the last type of bond, metallic bonding. So you guys know that metals conduct electricity. Wow, that's such a cool fact, dang. Like, you know, copper wires, they're kind of epic. They conduct a lot of electricity. And then these guys just got like 2 electrons hanging out. Now, because these electrons are so mobile in metals, like they're so willing to give away their electrons, once they come together, they just share their electrons like nothing ever happened. So instead of these electrons being associated with certain atoms, they're just floating around all around them. They're just like floating all around here, there's electrons all around here, there's a bunch of minus charges all around here. And then these nuclei, which are protons and neutrons, just have a 2+ charge. So you could think of these metallic bonds as a sea of electrons that are just holding these positive charges, which are attracted to the negative charges. So basically, a common question on the AP exam is like, what characterizes a metallic bond? They literally ask that. Make sure you say the words sea of electrons, because they really like to hear that. It really makes them happy, okay? Alright, we will talk about the property of the metallic bonding a little later, but first we got to talk about electronegativity. So we already touched on electronegativity in the Unit 1 review, but basically electronegativity is how much an atom hogs an electron. So if you have a bond between 2 atoms, there's basically 3 options, right? The first option is that both of them are equally electronegative. So for example, that's going to be a carbon with another carbon. Basically, they share their electrons equally, so it's called a non-polar covalent bond, because it doesn't shift to any specific pole. Then the other case is one has a slightly greater electronegativity than the other. So for equally, it's like approximately the difference is less than 0.4. These numbers are pretty arbitrary, but just know if it's a small difference, you could essentially say they're equal. But if they're slightly greater than that, not very equal. I always thought that the difference for this case is between 0.4 and 1.4. Then basically you can have like H and F, and then they're bonded like this. However, the problem here is that fluorine has a significantly higher electronegativity than hydrogen. So fluorine starts yanking these electrons over this way. So basically fluorine gets a tiny negative charge because it's keeping the electrons for a longer time than hydrogen is, and hydrogen gets a positive charge over here. And because you're shifting over the charge to one pole, but it's still a covalent bond, we call it a polar covalent bond. And then the last case, as you might expect, is very different electronegativity. So in this case, you could guess what it is. It's greater than 1.4. So if you looked at an electronegativity chart and the difference between electronegativity is greater than 1.4, you would fall into this case. So one example of this case is sodium and chlorine. So we basically know that metals over here are extremely not electronegative because they want to get rid of their electrons at all costs, so they don't hog it at all. The halogens, on the other hand, are extremely hoggy. They're such meanies. They want to have that electron so bad, so they have a really high electronegativity. In fact, they're so greedy that they snatch the electron entirely from the sodium, right? So then they form ionic bonds, as we already know, because NaCl is an ionic bond. Very cool. So basically, that's what you have to know about how electronegativity relates to bonding. Alrighty, now that we know the basic chemical bonds, now we got to talk about the different types of solids. Now, the reason why this is relevant now that we talked about chemical bonds is because the type of chemical bond determines what type of solid it is. So the first type of solid we got to talk about are molecular compounds, which basically only have covalent bonds within the molecule and not between different molecules. So the best example of this is basically going to be dihydrogen monoxide, otherwise not known as water. Basically because you have your OH, right? And you got another H over here. And basically they got a minus charge on the oxygen and a couple plus charges here. And when it becomes solid, they start aligning up. So then you have your H over here, you have your O over here, you have another H, and then you have another one over here, there's an O over here, and then there's like H over here, H over there. And basically like it crystallizes and these different things attract each other. There's another one over here. And basically it forms a crystal through these forces between the negatively charged oxygen and the positively charged hydrogen. Now these molecular compounds, the forces between the molecules are super weak, right? Because these negative and positive charges are only partial charges, okay? They're not like full-blown charges. They're only partial charges because oxygen has a little bit more electronegativity. So these molecular compounds have really low boiling points, really low melting points, and like they're easy to break. So think about ice as your core molecular solid, and you can basically just derive all of your understanding of their properties through ice, right? It has low melting point, low boiling point, and it's really easy to break. However, there is a different type of covalent solid. It's called network covalent. Wow, a covalent solid called network covalent is crazy stuff. But actually, it's kind of cool, honestly. Dude, during this AP Chem test, I screwed up a whole page on this kind of stuff. Oh my god, this is so bad. I literally said like molecular for half of the network covalent ones. So a really good thing to know, as I could tell you from experience, is the difference between network covalent and molecular. So molecular has covalent bonds, so does network. However, molecular does not have covalent bonds between molecules. Network covalent, however, has covalent bonds between every single part within the salt. Like if you know diamond, right? It's super hard. You know why this is hard? Because it has really strong bonds between all the atoms. If you basically got like a bunch of carbons, right? There's like carbon here, there's a carbon here, there's a carbon there, there's a carbon there, there's like carbons everywhere, and they're all interconnected with these covalent bonds over here. And as you said, covalent bonds are super strong. So the network covalent bonds, because they're all interconnected with only covalent bonds, they could have crazy molecular formulas like C60 or something, and they're super strong because they're made up of only covalent bonds. So these guys melt at really high temperatures. Boiling point is like out of this world, so I don't even think they would ask that. Basically just know that network covalent are your diamonds, okay? Super strong, only one element. Well, I mean, they could have other elements. Okay, this is one that I messed up really badly. SiO2, don't forget that SiO2 is a network covalent solid, because I did not put that, and I lost like 600 points on my AP Chem test. And then it's connected to another Si with a covalent bond, and then more oxygen. Oh my god. So much PTSD, god dang it. So these are your network covalent bonds. Just remember that diamond is a very good example of it. Also silicon dioxide. Alright, next up. Okay, we've already covered all the covalent boys. What do you think's next? That's right, ionic. Let's go. Ionic solids. Okay, so the perfect example of this is NaCl. Now these guys are really easy to visualize, right? Because basically you have your NAs attract to your Cl minuses, and then your Cl minus attract to your Na, and then they just form a lattice of a bunch of these ions over here. And now these bonds are way stronger than molecular because they don't only have partial charges, right? They don't only have these really weak intermolecular forces. They have ionic bonds, which are full charges and they're fully attracted to each other. Not as strong as like covalent bonds and network covalent solids, but really strong. Now what's really nice about the ionic compounds is that they're soluble in water because they're charged, right? So anything that's charged or polar could be soluble in water. So essentially when you put this in water, it dissolves into all its ions. And then these ions could carry charge. So they basically conduct electricity once they're put in water. So you gotta know that these guys are strong, but not as strong as network covalent. They're also soluble in water, and they also conduct electricity in water. However, they do not conduct electricity outside of water because once they're in a lattice, they don't move at all, okay? They're stuck in the lattice and the charges can't move at all. Just to go back a little bit, like for molecular compounds, like solubility depends on the actual compound, and then network covalent, it doesn't dissociate in water because water cannot break those covalent bonds. Basically, none of the ones that we've talked about already conduct electricity in solid form. Now, one more thing before we move on to the last type of solid, we gotta also remember that these guys are really brittle. Like, if you look at a salt particle, right, you could like slap it and it'll break in two. Now, the reason for that is like, think of these guys as like two separate planes, right? There's like a bunch of Cl minus over here, Na over there, and there's another plane over here. And basically, when you break something, you gotta shift the planes from each other. So when you shift this guy up, right, this Na is going to go right next to that Na, and then they're going to push each other apart. So even if the thing moves a tiny bit, it's going to go, it'll push and then it'll go out. So that's why ionic solids are really brittle. Okay, now we got to talk about the last boys, the metallic compounds, okay? Now these guys are just basically anybody who has a sea of electrons, and like your copper 2+, copper 2+, and then a bunch of E- things floating around. Now the main thing that characterizes these guys is the sea of electrons I talked about, and the AP likes throwing around that phrase a lot. Okay, so properties of this, it conducts electricity very well. That's because all of these electrons are just moving around, so they could easily move charge from one place to another. They're not soluble because, like, have you tried dissolving a metal in water? It doesn't work. Not quite. They're really malleable, right? Because if you move this Cu2 plus over here, or like if you slide it up, it's still gonna have this whole sea of electrons, right? You could think of it as like a magnet, like two magnets stuck in a pile of dough, right? Like the electrons are like the dough. You can still move the magnets around without actually making it push apart and break. The dough holds it together really well. I don't know why I said dough. It's more glue, but like dough is like the consistency I'm trying to get. Dude, it sounds like a cook. Dang. I should make a cooking video. That would be a great idea. Now, metals have a couple of interesting trivia points you gotta know. So, first off, the first thing that contributes to metallic compounds are compounds with high metallic character, which, as you might expect. So basically, like, as you go down the periodic table this way, you're getting more metallic character, because these guys over here are really willing to give up electrons and make that sea of electrons. Now, of course, you're not going to get pure francium metal because it's so reactive in air, but like, in general, as you go this way, your electrons are going to be way more free, and thus you're going to have more metallic compounds. Now, you also got to know how alloys work. So basically what an alloy is it's a mixture of metals. So a good example of an alloy, I kind of forgot all my nonsense, but don't worry, I'm pretty sure about this. Copper and zinc make brass. Am I right? Wait for it. Dude, my Quizable teammates are going to roast me, dude. I should know this. Copper plus zinc. You know what? Brass. Let's just search brass. Let's go! Copper and zinc! I'm so good. Okay, I'm not good at this game. I should have known. Whoops. But yeah, so copper and zinc make an alloy if you mix them together, and that's called brass. Bronze is if you mix copper and tin. Right? Primarily copper. Copper and nickel? Oh, that doesn't really not have like a specific thing. Yeah, tin, let's go. Let us absolutely go. I'm so good at this. Okay, I'm not. I'm so sad. Well, anyway, the point is that alloys are basically mixtures of metals that are really useful because they have new properties that are completely different from the other metals. They could increase their melting point, they could be more malleable, less brittle. You could change a lot of the properties just by making it into an alloy. So what you basically have to know is that there's two types of them. There's interstitial, and basically interstitial means that if you have a bunch of copper 2 plus ions that are like hanging out here, and they form a kind of a lattice over here, then interstitial means that your other metal, like in this case, let's say tin, is going to be in here. And it makes sense, right? Interstitial, the other thing is in between like the cracks. The other type is substitutional. And then this one also makes a lot of sense because if you have your same like grid over here, instead of putting it in between, it basically takes one out and it completely swaps it with like tin, okay? That's a substitutional alloy. So just know that like if you have interstitial, it's in between the cracks, but substitutional means you actually swap out a whole copper atom with like the new element. Okay, I think that's all we got to talk about solids. Let's move on to the fun stuff of dot structures, which are very fun, I must say. That homework for the dot structure thing took me so long, dude. Drawing it is so yucky, it's not even funny. Okay, dot structure, let's go. So basically, let us just do an example to review this. So like, let's say you have, what's a good example? What about CO2? So basically, in order to draw the dot structure, you have to know kind of how the molecule looks. So I already know that carbon is a central atom, and you could generally assume that carbon is going to be the central atom because carbon is kind of OP. So you put carbon, you put oxygen, you put another oxygen. Then for each bond, you put 2 shared electrons, which we know because they're covalent bonds. And then we fill in the rest of the space with electrons so that each element has 8 electrons around it. Okay, epic. We have oxygen has 8, carbon has 8, oxygen has 8, and then basically we have to count how many valence electrons this compound is supposed to have. So carbon has 4, and both oxygens have 6, so we add 2 times 6, and we get 16. So we should have 16 valence electrons. Let's count how many we have so far. So we have 6, we have 8, we have another 6, now we have 20. So we have 20 right now, we've got to get rid of some. So the way we get rid of them is we form more bonds. So in order to form a bond, you erase an electron pair from the 2 atoms you want to form a bond from, and then you add in another 2 dots here. We're still at 18 right now, so we got to delete 1 more. So what we're going to do is we're going to delete these 2, and we're going to make another bond here. Okay, epic. So now we know that we have O, we have 2 lone pairs, which are basically represented by these, and then you have 2 bonds over here. Because each of these pairs of electrons represents 1 bond, and then each pair of these electrons represents a lone pair because it's not paired to anything else. Hence, it's a lone pair. Alright, just a couple exceptions to this rule, basically. Like, drawing 8 electrons around it is basically boron, right? Boron is going to have a trifluoride. In this case, boron only needs 6 electrons around it. So, like your dot structure is going to look like this. I know boron doesn't have a octet, but boron is totally okay with that. The other exceptions where basically are ones that are really big, like SF6, like basically you draw it out, right? So you have S and then connected to 6 F's. And then how many valence electrons is it supposed to have? It's supposed to have 6 plus 6 times 7 is equal to 48. Right now I have the perfect amount. So even though sulfur has 6 bonds around it, that's okay because sulfur could form like extra stuff. It's called an expanded octet. So just remember those exceptions to the dot structure rules and you should be chilling. Okay, let's use a CO2 example to demonstrate formal charges. Okay, so you have CO and then like this and then like that. So basically your formal charge, the way I like to do it, is you take your valence electron. So for carbon, you would do 4, and then you subtract the number of bonds and the number of lone pairs. And then you subtract the number of bonds, and then you subtract the number of other electrons that are not bonds. So for carbon, it's pretty easy, right? Because we just got 4 bonds surrounding it, so its formal charge is just going to be 4 minus 4 is equal to 0. However, for oxygen, it's kind of epic because you do 6, and then you subtract the number of bonds, and then you got to subtract the lone pairs, right? But oxygen has 2 lone pairs, which have 2 electrons each, so it has 4 lone pair electrons. So we subtract 4 and we get 0. Epic. So the idea with formal charges is you want to get them as close to 0 as possible, and if you have to have a negative charge, put it on the most electronegative element, because the electronegative element is supposed to hog electrons and thus have a negative charge. Another way I like to think about this is like if you draw a circle around here, like around the element, you should basically think about each bond as having one thing here and one thing there. Then you just count how many electrons are within the circle, and in this case, oxygen has 6. And they subtract that from the number of valence electrons. So one good example of this is ozone, right? You basically have your 3 O's connected to each other, and then you draw your H around everything. So now everything has 8, and then you know it's supposed to have 18, but right now it has 20, so we had to get rid of one pair over here, one pair over there, and make a double bond. Okay, so now you got a double bond here. Now, however, this bond doesn't necessarily stay in the same place, because this bond could either form between these two, or it could form between these two. It doesn't really matter. So basically what happens in the atom is that this bond just shifts over here really quickly, and it switches between these guys really quickly, and it keeps switching which side it's on. And that's why it's called resonance, right? Because it's like vibrating, right? It's going from one side to the other. It's just forming different bonds at different times. But the problem is we can't show that in a dot structure. Like, this thing does not suggest in any way that this bond is moving around, which is why there are 2 ways to draw the exact same structure. You could draw it like this, with another double bond here and over here. This still suggests that this bond is vibrating, but it just drew it in a different way. So these 2 Lewis dot structures are called resonance structures, because neither of them completely show the full picture, but if you know that both of them exist, that shows how resonance works. Also, just a note, like, the bond order here is not going to be 2, because this is not necessarily always in the same place. Essentially, you have to take the average over all the resonance structures, so it's 2 plus 1 over 2, so the overall bond order is going to be 1.5. Alright, now we just got to talk about Vesper and hybridization. So first we'll talk about Vesper, and basically what this stands for is valence shell electron pair repulsion. So essentially, we had to deal with electron pairs. So basically, I'm just going to take the diagram off of the IB Chem helper, because basically, it's just memorizing a bunch of random different names. So let us just look at it together and try to make sense of it. So basically why it's called valence shell electron pair repulsion is because it tries to repel each other as much as possible. So if we just go through this and try to make sense of it. So the first one is you have 2 bonding electrons, right? So the diagram in this case is BS bonded to F, and basically the bonds want to push each other as far as possible. So they end up with a bond angle of 180 over here. Then if you have 3, the first option is if you have trigonal planar. That means that you have 3 bonds, and basically in order to get as far apart from each other, they had to do a 120-degree angle. Now you can see that in this case, the electron distribution is different from the molecular geometry. The reason for this is because electron distribution pretends like everything's the same. Lone pairs and bonds are exactly the same, but they're not. Lone pairs repel things a lot more. So in this case, to get bent, you have 1 lone pair over here, and it repels it more, so it pushes those 2 other atoms together, and that's why your bond angle is less. Then for tetrahedral, meaning you have 4 pairs of electrons for your electron distribution, there are 3 molecular geometries within that. So tetrahedral means you have 4 bonds. Basically, whenever you have only bonds, it's going to be the same as your molecular geometry. But if you start adding electron pairs, then you're going to have a pyramid, because this diagram is not very useful, but like if you have N and then you have 3 H's out, the lone pair at the top is going to push everything else down. So the reason why it's called a pyramid, it makes a lot of sense, and it's really easy to remember if you think about it this way. Look at what these guys look like. They look like a triangular pyramid. So trigonal parameter. Okay, and then for bent, you know that water is bent because it has 2 lone pairs, and these lone pairs push the other oxygens down. And because it's only an H to an O to an H, you can think about it, there's a bend, right? And there's nothing over here. So it's not a triangle, it's not trigonal planar, it's just bent. And the more lone pairs you add, the smaller the bond angle is going to be. Now things start to get a little bit whack once you start adding to 5 pairs of electrons. So the reason why it's called trigonal bipyramidal, or the way I like to think about it, is if you have F, P over here, another F over here, F down there. See, there's a triangle here, and then there's one pyramid up here, right? There's a pyramid there, and then there's another pyramid down there. So it's trigonal because the base is a triangle, and then it's 2 pyramids, so bipyramidal. Seesaw because if you draw it like this, basically your 2 legs are here, and then you got like one over here, and then it wiggles like that. Very cool. You know what this thing's called? It's called a fulcrum, that's right. And then the last one is just T-shaped, which makes also a lot of sense because it's literally just a T-shape. In this case it's Cl, another F over here, another F over here, another F over here, and then lone pairs over here. So if you only look at this part, it looks like a T. Very cool. And then basically the other things are the same concept. Okay, lastly, just to quickly explain hybridization. Basically, in order to make these bonds, you have to have orbitals for the electrons to share between each other. So in order to get 2 bonds, basically what happens is your s orbital and you have your p orbitals over here. One of these p orbitals joins with one of the s orbitals, so you take out one here, you take out one here, and now you have 2 of these orbitals that need to be put somewhere else. So they come together, there's 2 orbitals, and they make themselves, they equalize each other's energy. So now they're over here in between. And these are called sp hybrid orbitals because they form between one p orbital and one s orbital. So perfect, now you have 2 electron pairs. So anything with 2 electron pairs is going to be sp hybridized. But what happens if I wanted 3? Well, you always had to take your s, so we're going to take this guy. But in order to get 3, we already took 1 line, but we need to take 2 more lines, so we'll take these 2 lines. So you take 1 s and 2 p's, they bring each other to the same level, and now they're called degenerate orbitals, same energy. sp2 hybridized, because you took 2 p's, made it with 1s. And see, we have 3 electron pairs, so we're sp2. So then these guys are going to be sp3, and then you got sp3d, because d got to get involved because you only have so many p orbitals to use. Then you got sp3d2. Nice. Now we understand hybridization. Basically what it does, takes orbitals at different energy levels, makes them equal so that they can finally form bonds. Okay, that's all I got for you guys today. Let me know if it was helpful. I know I didn't completely explain Vesper, but I wanted to explain how I thought about it so that it would be a lot easier for you guys to remember. But other than that, that's all I got. Thank you guys for watching. As always, if you enjoyed the video, leave a like and subscribe for more. Let me know what I'm doing right. Let me know what I'm doing wrong. You guys have been liking the videos in the past few weeks, so thank you guys for that. Thank you guys again for watching, and see you guys next time.